look great, Miss Jenkins.
Oh! Plus one of my heart. All right. So here we go. We're actually live. Shout out to Seb. Everybody else.
Hi, Seb. What do you mean live?
Here we go. Happy birthday, Alec Backlash.
Wait, is this live?
Lots of happiness in the room today. No, we're not singing yet. We're not singing. We're on tape. All right. I got 3 parts to do today, and let's see. So part 1.
Hey, Seb.
Hey, Seb.
Seb, you got this? You getting this?
Sebby.
So part 1, we're going to be talking about infinite series today, pretty exclusively. And what happens when we combine infinite series? It may surprise you. It may not be exactly like what you think. So what does that mean? So like example 1, I'm just going to go right into an example and not really talk about the theory behind it. Let's see, I have an example all worked out right here. Summation k equals 1 to infinity of 4 over 7 to the k power plus 3 over 2 to the k minus 1 power. Okay, not a very pretty example, but this will do for us. So now we have, really this is 2 infinite series, right? We're plugging in one. I could rewrite this as k equals 1 to infinity of 4 over 7 to the k power plus k equals 1, 3 over 2 to the k minus 1 power. So any intuition about these infinite series? What do you guys think? Convergent, divergent, blah, blah, yeah.
I would say convergent.
And you would be right.
They're both geometric.
Oh, I'm out all the candy, but you totally deserve some. So plus 1 in my heart. You guys are going to get a lot of those today. That's right, they're both. But what about this k and the k minus 1 business? And what? That's not to the k power and doesn't look like a normal ratio a times r to the k. Can you help me? Can someone do this for me? Let's rewrite this so it looks a little more familiar so we can use that sum formula we have, right? So how can I rewrite this? Well, that's the a, isn't it?
Yeah.
So I'm just going to pull that ahead. And then that's 1 over 7. Well, now can't I just put that k out here?
Of course you can.
Of course you can. I know, so easy. Math is so beautiful, right? So that I just rewrote that so it's very clear that this is my a times r to the k, where r is, the absolute value of r is less than 1. So we know that that converges. And you guys know the formula to find that.
Yeah.
You can actually use a formula. Now this one's a little trickier, isn't it? Plus k equals 1. So I know I can pull this forward. 3. Yeah, what is this? 3 over, oh, let's do 2k.
Why'd you put a 3 up there?
Oopsie, didn't mean to. Thank you.
Hard point.
Who was that?
No one never takes his own nerd points.
Noah plus 1.
Wesley has like 30 of them.
No, you get a nerd point, Noah. Thank you very much. That's, of course, what I meant to write. Thank you for, I don't want to make any mistakes here. Thank you. So now, am I good here? Right? So I did, this is the same as, because it's to the 2 to the negative 1 power, this is 2 times k times 2 to the negative 1 power, isn't it? Right? So do that, and then do this, and then how do I rewrite this? What's my a?
6.
Denominator and the denominator becomes a 6. Yeah. So that's 6. So I just wanted to give you guys one example of how that works.
That's kosher?
Yes. Yeah. Because this is just to the 1 power. You know, I made this 3 over 2 to the k over 2 denominator, and then denominator becomes a numerator.
Oh, so we can always do that.
You can always do that.
Like,
so don't be freaked out if you have like this k minus 1 thing. Break it down. You guys know your rules of exponents perfectly, right? So Colin's intuition was perfect. When you have a convergent series and you add another convergent series, you get a convergent sum, right? Okay, that's obvious. So now, example number 2. Too late. Sorry.
And that's just rule number 1, right? So when you add 2 convergent series, you get a convergent series.
Yes. N equals 1 to the let's do this. 5 over 3 to the n plus. Let's do that one. So convergent or divergent?
Divergent.
It is. I'm gonna give you something fabulous. I don't know. I'm not a normal. I can't be my normal teacher without my candy though. I'm sorry, but I do owe you candy. So.
Are you not doing candy because you're on TV?
No, because I'm out.
Oh.
It's on video, so you can.
I know. There's proof. There's proof for the world to see. So, Alec Mackless, you are on fire on your birthday. Perfect. That one, you guys are cool with. That's a geometric.
Yeah.
But what's wrong here? Oh, the placement of that N, right? Yeah, go ahead, George.
It's greater than 1.
Yeah. That being, you know, outside with the 5, inside makes all the difference because now my ratio is greater than 1. Or equal to 1, greater than or equal to 1. Okay, so that diverges. So you have a convergent plus a divergent always diverges. So convergent plus divergent equals divergent. Looks like dirge, the birthday dirge we sang to Alec. I always think that's a sort of mournful song. Can I erase?
Wait, it's called the birthday dirge?
Well,
It's
that's
called
like
a birthday song.
You know, that's like a dirge, like you
The funeral
walk
march?
to your funeral march. I think it's a very mournful song. It's not happy. All right, so example number 3. What do you think you get when you add a divergent series to another divergent series?
It diverges.
You would think.
Wait, but you said before that infinities can't cancel. You said infinities can't
I
cancel.
know I did. I know. 99.999% of the time, divergent plus a divergent diverges. But
Unless
what
it's
about
the
this?
exact same thing.
Now, the thing is, you can do algebra here, can't you?
Yeah, that's 0.
That's 0. So officially, you could rewrite this as 2 divergent series. So, okay, the vast majority of the time, divergent plus divergent is divergent.
So that like the only case where.
You just have to think about it. Don't just rush ahead. It's the only case. It's the only case.
Oh.
Just want to tell you. All right. So the moral of the story: convergent plus convergent is convergent. Convergent plus divergent. 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 Just check.
It's like a dominant trait.
Yes. I know. I know. It's very good. You guys are so well educated. Line High has done well, you guys. All right. So that's part 1. Part 2. What's part 2? Okay, the divergence test. Now, you did this in your classwork yesterday, yes?
Yeah.
Yeah.
No? No? Maybe?
Yeah.
If you didn't, that's okay. I'll cover it now.
Today? Yeah, there's the notes and stuff.
Oh, like the ratios.
Yeah.
Subtracting.
Yeah, man.
So that's increasing.
Oh, you're right.
Okay, so with these infinite series, like you can solve it when you can do a telescoping series, you can find a value, or obviously a geometric infinite series. The vast majority of them we can't solve, right? It's like infinite. We can maybe find a limit, but we can't actually solve for most of them. And if you look in the beginning of, if you guys read the chapter, in the beginning it's like, there are many applications of this in engineering and mathematics. I don't know them. I don't know, you have to look it up, but I assume that this has a big place in the world. I don't know, maybe I should admit that, but I don't know its practical applications. But what we want to do is we want to say, can we find an answer to this? If it diverges, we can't. So let's not even bother, right? So let's just figure out, does it diverge or not? So, well, let's look at some partial sums. What's S sub 1? Yeah, 1 over 1 plus 1, which is, what's S2? And don't just do it plus, 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 don't add it. 1/2 plus 2/3. What's S3? I'm going to do S2 plus 3/4, right? True?
Correct.
So now, what happens when it's S100? Isn't that S99 plus 100 over 101?
Yeah.
Yep.
Right? So do you see, I'm always taking the previous sum and adding almost 1.
Yep.
So I'm always growing bigger by 1. So this can never converge because you're always increasing. So a down and dirty way to check and see, and do this always, please, is take the limit. Fire today, man. You're on fire. So number 1, if you are asked this question, question, right away, I want you to take the limit. And you're going to take the limit of the general term. So take the limit of the general term right away. You're going to learn about 8 convergence tests, and some of them are very confusing and complicated. Go easy, baby. Go quick. The limit as n goes to infinity of your a sub n. If it's not equal to 0, there is no way that this will converge. So it must equal 0 for us to consider that it converges. If it does not equal 0, does not equal 0, the series diverges 100%. So you're done. So in this case, we do, this is all the proof, and these are proofs, like 1 AP, they're proofs. All you have to do is say the limit as n goes to infinity of n over m plus 1 is what? 1. Thus, this of course I'm off my, sorry Seb, I'm off the thing, diverges, and then you have to do QED, code erotic. Right? Alright? That's all you have to do. It's so simple. Divergence test. Really, but you guys, if you get 0, it does not mean it converges. It's called the divergence test because that's all it proves. Divergence. There are series, the limit of the nth term goes to 0, but they still diverge. Yes, it is.
Wait, what? Which ones do?
You'll see. Okay? Can I erase?
How can that happen?
I know. It's so counterintuitive, I need to prove it to you, I think.
Yep.
All right. So I think that's it for the divergence test. I think that's all we're doing. Okay, part 3. This is the last part, and I know I'm doing a long lesson today, and this one depends on how you guys are with this. Will take about 10, 15 minutes, depending if you're convinced by my argument or not. Okay. Part 3, the harmonic series.
Oh, unless Miss Jenkins, it's already in 2 separate prongs. Is that it?
So, I have a lot of musical people in this classroom. It's so lovely to have all these musical people. So I had a friend of mine was a physics teacher, and he did a PhD on the physics of the guitar. Right? It was kind of interesting. And when you pluck a guitar string, what do you think those vibrations weaken and they get down to 0, right? You would think they get cut in half. They don't. You have the full strength, and then you have a half, and then you have a third, and you have a quarter of the strength, and you have a fifth.
1 over.
This is why it's called the harmonic series, because of the physics of music with with plucking strings. It can be violin string, cello string, which is weird, right? So the crazy thing is this diverges. If we have n equals 1 to infinity of 1 over n, what's the limit? Let's do the divergence test. What's the limit as n goes to infinity of 1 over n? 0, clearly.
Yeah.
But that does not prove convergence. It just means we can't use the divergence test. You might want to say the divergence test is inconclusive. Inconclusive. It only works when you get anything but 0. Okay? Is that clear? I hope that sits in with you guys. So inconclusive. So now we have to think about other things. And we're going to go to Riemann sums to prove this. Remember that? Yes.
Unfortunately.
Unfortunately. The divergent test is inconclusive.
Oh, is that what that symbol means?
What?
Oh, I just have terrible writing this.
No,
Zero. That's a 0. That's really bad that someone doesn't know when I write 0. Ms. Jenkins, be more careful. Okay, so now here goes the proof. So, one, two, three, let's make this not quite to scale. I'm going to make this one bigger. That's 1. Is that okay if I make that big? So when n is 1, we get a dot at 1. When n is 2, we get a dot at 1/2, and then a third, and a quarter here, and then so it's like this. Now we don't connect the dots, right? This is discrete. This is discrete. I always want to connect the dots, but we're talking about what's our domain for these things? Positive integers, right? So we don't get this stuff in the middle, even though no, I want to connect the dots. So the funny thing is, you guys proved that this 1 to infinity of dx over x, you proved what when we did that when we did improper integrals? Converges or diverges, right? Are we still on? I don't know. Okay. So this diverges. You know this diverges, right? So I'm going to use that information to prove that this diverges also. See how it goes. I'm a little nervous. I don't know if you guys are going to like this. Rolling up my sleeves here. Oh. Okay. So onward. All right, I'm going to connect the dots a little bit. I'm going to make rectangles.
Yes.
I think I missed it.
Right.
Oh.
That's okay.
Ms. Jenkins, how
Yes.
do we prove that, that integral again?
So you get ln x, right? When you do, you take the limit as t goes to infinity of 1 to t of 1 over x dx. And then what's the integral of that? ln, yeah. So it's the limit as t goes to infinity of ln t minus ln1 and then infinity. So this, you can just use calculus to show you get, I mean, that's that new lesson you guys learned last.
That's so brutal. 'Cause that makes no sense looking at it.
I know. I know. All right, so if I have rectangles with width equal to 1, what is my Riemann sum with left endpoints? So I have a rectangle, so what's the area of this rectangle? It's 1 times 1, right? Plus 1, my width, times, what's the height for this? 1/2. Plus 1 times, what's the height here? A third. You guys seeing what's happening? No. No? No? You're going to put me into a state of utter dismay
Oh my god, it looks
and
the
ruin?
same. You're always adding some value.
So
Except for when you're adding
the
like
problem
1
is,
million.
this
But you're
Riemann
still
sum
adding
goes
one
to
million.
infinity, but can't I represent this as a Riemann sum? It's the same numbers,
Yeah.
right?
Yeah.
It's a different concept, but it's the same numbers.
But the
You're
Riemann
always,
sum
you're,
is still
because
an
you're always
approximation,
adding
it's still
something, you can
divergent.
never add, you can never have,
No, but they keep on
you can never have a,
Oh, the Riemann sum.
I know, but you can never have a value L that it can't exceed, even though
yeah,
if
you can because those little numbers don't like 1/1,000,000 plus like
We can't
1/1
find this.
million.
Yeah, we can't add that up. We don't have the math skills to do that. Like, it's not possible.
Oh, and the
So, but what you guys do know is I'm gonna connect these dots. I
Riemann
said I
sum is
wasn't going
greater.
to.
it's greater than that
Yes.
integral.
Yes. No.
Yes, Noah.
Plus 2.
11.
Ah,
Yeah.
Yes.
Noah had taken all the nerd points that he actually deserved. He would have had like 30 from the first and second quarter.
You know what? You gotta
He'd be tied
take
to
what's
me.
yours.
He
You
would
gotta
have
lay claim to what's
21
yours.
more.
Do you guys agree with me? The area of the Riemann sums is larger than the integral. It's crossing over that line, isn't it? I've got leftovers.
You can beat up me.
Isn't that Riemann sum larger than a known divergent series? Integral?
Oh.
Woo! It's all coming together! It's all coming together. I know.
Right, say
You
that again,
just
I missed it.
proved that this is larger. This doesn't fit right here very well.
Oh my
L sub n is larger than 1 dx over x. It's bigger than something that we know diverges because those rectangles hang over the curve.
Makes so much sense.
And that ln is the harmonic series exactly. we can't find a sum of it, obviously, because it diverges, right? And we can't even begin to ever hope to find, this. The way we add up Riemann sums is to take the integral of them, right? To do infinite ones. But as it stands, if they have width 1, it's larger than a known, and thus, here there are many ways the harmonic series must converge. Diverge, Miss Jenkins. I'm on tape saying one thing. Must diverge. Must, because it's larger than a known divergent value. Yes?
So what other...
This is the big one.
Yeah, this is the big one?
This is the big one. This is the really big, weird one that's a ratio with x in the denominator and 1 in the numerator. And you're going to learn more about it in your lesson today.
So the reason that a lot of other series aren't like this are because they're telescoping, right? And cancel. So what other, are there any other ones we really have to know, or do we, should we just, so we should just kind of mentally note that if it's not the harmonic series, we can be pretty confident that...
No, I'll get more into it, and you'll learn more in your classwork. But that proof work for you guys?
Yeah.
Okay,
Yeah.
I have one last little thing to do, and then you're on your own. I'm sorry I'm taking so long. Yeah, Grace, and then George.
Actually, I'll ask.
Okay, thanks, George.
So then you can use this, the harmonic series divergence and use it to prove that others.
a good 15 minutes.
Yes. Yes. Excellent. This is going to be like the foundation. That's excellent, George. This is going to be the foundation of much of our work in the next 2 weeks. Okay? So the last thing I want to show you guys is... This proof is not in your book, by the way. I hope that made sense.
It was so confusing.
Was it?
They did like squares, like 1 over 2 to the end.
Yeah, I don't like that one that much.
It was so confusing.
But that makes sense, right? Super clear, super
Yours made
geometric.
sense.
Yeah, so now, I guess, oh gosh, there is a part 4. Did I say there were only part 3? I did. There's a part 4. I'm almost done though. Is it hot in here? A little bit. Okay. So the integral test. This is weird, but it follows up right on the heels of what I just did. So given some infinite series. Now, if n equals 1 to infinity of a sub n, if all the terms are positive, all right, if all the terms are positive, and if it is decreasing, or eventually will start to decrease, or eventually is decreasing, steadily decreasing. And you guys did that in your notes.
The term is
The terms, yep.
Jenkins,
steadily, not steady.
proofread, you're on film.
Thank you. Steadily. I'm always jumping ahead while I'm teaching, so, and, yeah, so if you have those things, so if you can do this, and you've got dots that basically look like this, in quadrant 1, decreasing, then you can compare this to an integral, just like I just did. It's the same principle, right? So you can compare this to an integral. Now, the values are not the same. So you can compare an infinite to of some f of x dx. Now, this is continuous. This is discrete. The values are different. I hope that makes sense. The rectangles that hang over the curve, they're not equal, but if this diverges, this will too. If this converges, this will converge. The behaviors are the same. Yeah?
I was going to say, if you were proving that with like 1 over x squared,
Yeah.
do like right endpoints and do, or how would
Well, so let me do an example, and then I think I'll be done. So, yeah, so. All right. Now this is in your packet, the exact, you don't have to write that whole thing down, it's on in the last page of your packet, on your package with the notes. So let's say, as an example, we want to prove n equals 1 to infinity of 1 over n squared converges. Do you guys have that in your packet?
Yeah, that's C, 2C.
No. Alright, so I'm doing your homework for you. So prove this converges. Well, you have to look at your a sub n term. Can you guarantee that from 1 to infinity, 1 over n squared is always greater than 0? Of course.
Yeah.
Your input's positive, you're squaring it. So that's checked. Is it always decreasing? Yes. And you can do that by taking the derivative and showing that it's decreasing. Right, you guys did that in your homework or your classwork, right?
Yeah.
So take the derivative and prove it.
So what is this?
Ms. Jenkins,
Prove that it's decreasing, yes.
you said that it just matters that it eventually is always decreasing,
Mm-hmm.
but it always has to be positive.
Yes.
It can't eventually
No,
be positive.
we need all the terms to be in quadrant one.
Okay,
Okay. So we're good. And now, what I'm going to do is say, well, what happens with 1 to infinity of x to the negative 2 power? Because I'm going to compare it. So I'm comparing a series, a summation, to an integral, right? This is so sloppy, sorry. 1 to infinity of 1 over x squared dx. And then you just have to take the antiderivative of this and prove, using your limit notation that we talked about last class, that that converges. And you guys can do that. Okay? And then you just take the limit, prove that, and since this converges, this also will converge. That's the lesson.